Yesterday lecture we have studied internal resistance of a cantilever beam to an applied torque. It has two parts. One is Saint Venant's torsion Gj into d beta divided by dz, and another one is the warping torsion E gamma into d cube divided by dz, right? And then today we will study that the strain energy of the torsion. Strain energy. I hope all of you know about strain energy. Strain energy is defined as the energy stored in the body due to deformation. The energy stored in the body due to deformation within its elastic limit. That also you remember, within its elastic limit. For example, normal beam. Okay, normal beam. I am drawing that load deflection diagram. X-axis we have displacement. I'm assuming delta L. Y-axis drawing the beam. That curve is up to that elastic point. Okay, that post elastic I have not considered. That plastic limit I have not considered. Now strain energy is the area under the load deflection curve, that is equal to 1 by 2 times P into delta L. Right. Similarly, torsion also we have strain energy. Okay. Torsion U is equal to 1 by 2 into T, that torque into beta. Okay. The beta is the angle. Beta is the angle. Even we can tell that small beta, small angle, d beta. Okay. Now I am drawing a circular rod. See that pure torsion or that uniform torsion, you can see only the circular cross sections. Okay, that cross after applying torque, that cross section will not change. There is a small change in the angle. Right here, I am after applying torque. There is a small change. That angle is called beta. Now I am writing Saint Venant's strain energy of a strain Venant's torsion. Okay. Strain energy of torsion we can divide it into two. One is the Saint Venant's torsion or pure torsion, and another one is the warping torsion. Okay. I already told you that pure torsion, okay, you can see in the circular rod, the DUSV is equal to 1 by 2. I am just rewriting the above equation, 1 by 2 into T into d beta. Okay, that small change in angle, I am considering d beta. So actually that same Venant's torsion is equal to 1/2 of the product of torque and change in the angle of twist. Okay, that I have considered small distance d. The change in angle twist I am taking d beta. D beta is equal to T by Gj into dz. Okay, this one from that torsion equation, T by J is equal to G beta divided by L. Okay, here L is equal to small, that is this. Beta is equal to small beta, that is d beta. Here T is the torque, G is the torsional rigidity, the first equation, and this is second equation. Now the value of d beta substitute in equation 1. Strain energy due to Saint Venant's torsion DUSV is equal to 1 by 2 into T square divided by Gj into D is it. This equation is called equation number 3. Again, rewriting the same equation, 1 by 2 into T square divided by Gj into D is it. Now, the value of T we know, the substitute the value of T in equation 3. Yesterday we have calculated. The total strain energy is equal to total torsion is equal to Saint Venant's torsion plus warping torsion. Saint Venant's torsion, that T, yesterday we have calculated, Gj into d beta divided by dz. Now the value of T we can substitute in equation 3. 1 by 2 into we have Gj into T square, right? D beta divided by dz, the whole square, into dz. Now we have determined the total strain energy. Integrating over the length gives the strain energy in the entire member due to Saint Venant's torsion. We integrate. Integrating over the length. Over the length gives the strain energy of the entire member. Now that strain energy, that's called Saint Venant's torsion or pure torsion. USV is equal to 1 by 2 integration 0 to L into Gj, the torsional rigidity, into d beta divided by dz, the whole square, into dz. This is the Saint Venant's strain energy. I'm calling this equation as the 5. Now we will move on to the second part, that is the warping torsion. We determine the strain energy of a bar. Warping torsion strain energy. Normally the open section, the warping will happen in the open section, okay, I section or channel section. For an I beam, the strain energy stored in the member the strain energy stored in that member due to its resistance to warping is assumed to be equal to the bending energy of the flanges. Bending energy of the flanges. It's the assumption. Okay. Now, the bending energy stored in an element D set, we consider a small element D set. The bending energy stored in an element D set of one of the flanges D set of one of the flanges of an I-beam is equal to the product of that's important. It is nothing but half into moment into rotation. Okay. Is equal to the product of one half of the moment EIF d squared x divided by dz square and rotation. Rotation d squared x divided by dz square into dz now duw is equal to half times EIF into d squared x divided by dz square into dz. This equation is called equation number 6. Now here that x is equal to lateral displacement. Last class also we determined that x, right? We have the angle beta. It is the height by 2. It's height by 2. That x distance, that's equal to approximately equal to beta into h by 2. Now I am substituting value of x, the above equation number 6. Oh, there I missed a square. Okay, moment EIF into d squared x divided by dz squared whole square. Okay, now the value of x I am substituting in that equation number 6. E into IF divided by height square divided by 4x square. Okay, height square divided by 4 into d squared beta divided by dz square into dz. Now we want to determine the total strain energy. For that we have to do the integration, integrating over the length and multiplying by 2 multiplying by 2. We have two flanges, that's why here multiplying by 2 to account for both flanges. That gives the strain energy of the entire member. Is the strain energy of for the entire member due to warping. Now UW is equal to 2 by 2. We have two flanges, 2 by 2 in direction 0 to here. EIF into height squared by 4 into d squared beta divided by dz square, the whole square into dz. This equation is called 8. Now we know gamma is equal to IF into height squared by 2. It's not 4. Height squared by 2. We studied in the previous class. The gamma is the warping constant. Okay. It's the cross-sectional properties. The IF, moment of inertia of the flanges, height, depth. That's called warping constant. I am substituting that warping constant in that previous equation 8. Your W is equal to 1 by 2, the height squared by 4. Okay. That 2 is coming here. 0 to L E into gamma into d squared beta divided by dz square into dz. Equation number 9. This equation is a very important equation. This equation gives the strain energy of the entire member, strain energy due to warping for the entire member, and then we have to determine the total strain energy. Okay. In a cantilever beam, we have pure torsion as well as warping torsion. The total strain energy in the twisted member is obtained by adding St. Venant's torsion or pure torsion plus warping torsion. Okay, strain energy due to warping torsion. Now U is equal to 1 by 2 into 0 to L Gj torsional rigidity into d beta divided by dz the whole square into dz, that is St. Venant's torsion, plus 1 by 2 into 0 to L E gamma into d squared beta divided by dz square the whole square into dz. The whole square is missing. This gives the total strain energy of the twisted member.